All right. Thank you. Good afternoon. I am Joe Harvey, and I'm here today to talk to you about post-quantum DNSSEC, specifically about routine performance and resilient fallback. Today, I'm talking on behalf of several people who've done research that we've compiled into this. Min Hong Tran, Bert Kaliski, Danny McVicker, Benno Oviander, Swapnil Sheth, and Andre Suri. Okay, so the algorithms that we have for DNSSEC today are at risk with post-quantum computers. Quantum computers could break them, so we need to do something about those signature algorithms. The standards that NIST came up with, FIPS 204, 205, and eventually the Falcon standard, all are post-quantum safe, but they have very large signatures, and that makes a kind of a problem for DNS where we have small packet sizes that we need to work within. So NIST has an additional competition going on for some additional signature algorithms. Those algorithms, though, are potentially have smaller signature sizes, but we don't know exactly what cryptographic assumptions they're going to have, and we don't know if or when those will even get standardized. So there's a little bit of a risk there. All right. So what do we need to do? We need to find our way. The first thing we need to do is find a set of algorithms, a class of algorithms that give us routine performance. Those could drop in and be similar to what we have today, if we can find some of those. And then also have a conservative algorithm that gives us a resilient fallback. The resilient fallback is in case there's any issues with these new cryptographic algorithms, we have something that can keep things together if we need to rotate or change the algorithms over. Currently, we really like SLHDSA simply because it's based on hash-based functions and is very conservative. Hash functions have been pretty well proven, but it does have some performance and size challenges. MLDSA and Falcon, the other things that have been standardized by NIST, are possibilities as well. We could consider LMS or XMSS. Those have state issues, though, so that might be hard for operators. But then finally, again, these have large signatures, so we may want to use something like MTL mode that reduces those impacts, especially for the conservative algorithms. And I'll talk about that more in just a little bit. All right, so considerations. There's a couple considerations. The first is timeline. So currently there's been the standards, the 204, 205. They're working on 206. NIST and other organizations are following a similar pattern to NIST, but they're going to deprecate RSA 2048 in 2031. And by 2035, they're going to disallow all of the classical algorithms that we use today, algorithms 8, 13. So we have a slightly less than 10-year time window until that point in time. But in the meantime, we need to consider how things are going with our keys. So like at the root, we publish a key for about not quite 2 years so that it can be incorporated into the software. Then it's used to sign for about 3 years. So roughly a 5-year window for each key while the next key is being published and then onboarded. So we're in the middle of rollover right now. If we look at that timeline, then we really only have a few chances to change the key and roll it over in the current process between when those algorithms are disallowed. Additionally, as I mentioned, we have 3 algorithms today, well, more than that, but 3 that are really widely used that fit and work pretty well. These other algorithms, the PQC ones, we don't even have one yet that will work really well. So we really need to be thinking about how we can find something that fits with what we have, works with the existing ecosystem, while at the same time not hedging our bets on just one algorithm that may or may not prove long-term to be stable. So we need agility. We need a way to adapt. And especially for things like the root zone where we have several years, we need something conservative as a backup so that if something happens, we're not scrambling to be unsecure and deploy a key as fast as we can. So before we get right to the research parts of this, what do we need to do? Well, we talked about this at the PQC DNSSEC side, mainly IETF, and we can't really wait for the NIST onboarding to complete because if it continues at the rate that the last one went, we'll have at most one chance to roll a new key and deploy it. So we need to find a way to do something with what we have today. We need to apply a diversity strategy, like I said, at least one conservative algorithm and at least one higher performance drop-in algorithm, and then use those to allow the operators to choose whatever works best for your zone. Not all the zones are the same, so this would give us a chance to have keys that we can use safely and also work within how the operators are operating. All right, so talking about the research now. So some of the research is done by Andre from the University of Ostrava and the ISC research. He looked at the potential low impact drop-in algorithms that are there. So he looked at NIST, Falcon. He looked at 3 that are in the additional ongoing scheme Hawk, SkiSign, and Mayo. And then also one called NTRAG, which is part of Asia Crypt conference. That's a size-reduced variant of Falcon. And so if we look at these charts here, these charts show the time it takes to do signing and the time it takes to do validation with these new keys. And as you notice, some of the new ones have red highlighting. So that means that they are significantly slower than the current algorithms. So that makes an issue for signing the zone, especially for validation, where the recursive is doing a lot of validations. Really slow algorithms can slow down the whole resolution process significantly. All right. Additionally, if you look at message sizes, so typically DNS is sent over UDP, where we have a limit in packet size of 1232 bytes. Maybe with eDNS options, you have a little less, a little more, depending on your middle boxes. But several of these, if you notice the SOA and the delegation record, these algorithms might fit in a normal response. But the DNS keys are very large, so you're going to get truncated responses for most of the DNS key queries. And also NX domain and no data responses also go over the limit. So some of these work okay for performance, but like SkiSign did not have the performance numbers we need, but does fit. So there's a lot of trade-offs here and nothing perfect that fits. So overall, Andre's conclusions, some of the large public keys might be okay. It might be all right to do a TCP query for DNS key records and have everything else be able to fit in the UDP packet. Overall, Falcon is slow and does require switching to TCP. Hawk looks like it might be possible. Mayo has a larger public key, but also might be possible in the other UDP packet sizes. And NTRAG looks possible. That would be one that's outside of NIST, so it might be of interest, but also it may not be standardized by any of the large bodies. Okay, and then in the conclusion there, so what else do we need to look at? We need to look at the attack vectors. So there's a lot of things with DDoS that having these larger keys and larger signatures could cause issues with. It could also be, again, if the validation is a lot slower, it could have a huge impact on the recursive resolver doing validation, and also how you want to configure these. We need to look at multiple levels of the DNS hierarchy. So root, TLDs, SLDs are all very different. Some zones change frequently, some zones don't. So we need to evaluate these keys in those contexts also. And then continue to look at and test new algorithms and see if we can find something that fits really well where like ECDSA fits today. Okay, so that kind of looks at the low impact drop-in algorithms. Now, if we want to look at resilient fallback, what can we do with the classical algorithms today to make it work? So some of the research that I've been involved with, we took a look at the NIST standard algorithms, look at the signing time. Again, you'll notice that these are all a lot higher than the current algorithms. SLHDSA does have a much smaller key, which is one nice feature, but the overall performance is significantly slower. And if we look at query and response, again, you saw in the previous chart that Falcon could fit in the 1232 bytes, but the other ones don't. So they will require retries for each of those or truncation for each of those queries. But it's actually amplified a whole lot more. It becomes a significantly larger problem if we look at NSEC and NSEC 3. So in an NSEC response, usually there are 3 RRs and 3 RR SIGs. It could be more, but they come back. And so we have only 4 of the algorithms that currently will work within NSEC and still fit in the packet size. If we look at NSEC 3, where we add an additional RR set and signature, then we get to even smaller set of basically ECDSA and SkiSign, which had the very, very slow performance. So there's still a lot of work we need to do looking at these with regard to denial of existence, because large is bad, but then large times 4 makes it significantly worse. So overall, nothing currently fits that's really great from the currently standardized algorithms. And like I said, we really need to look at NSEC and NSEC 3 and see what we can do to optimize it. So based on that, we looked at modes of operation. How can we improve with what we have today and try to make it work within the constraints that we have? And so first, just a little background. MTL mode is a mode of operation that we came up with around how to use a Merkle tree to try to amortize the cost of those large signature algorithms. What you can do when you have an expanding set like DNS where we keep signing more and more messages is you add them into the tree and the Merkle authentication path becomes your validation path. You still need to verify the root. So you take each of those roots, package them together, and sign them with a post-quantum algorithm. And so in that case, you only need to do the post-quantum cryptographic operations once to verify the latter. And that gives you a bunch of roots to verify. So you can verify everything else in the tree using that one set of roots. And you don't have to redo the large signature for each of those. All right, so Internet Labs with the University of Amsterdam took a look at MTL mode and did some evaluation of that. There were 4 questions they were looking to answer: the impact of MTL mode on SLHDSA, how does it affect the key sizes, how does it affect the excuse me, how does it impact the verification performance, and then overall looking at that compared to ECDSA so that we have a basis for comparison. All right, if you look at the chart here, you'll see table 1 shows what the signatures were with the condensed signature, the authentication path. So if you look at SLHDSA, you'll see that it's 7,800 bytes. That's roughly just the size of an SLHDSA signature. If we can use the authentication path from the Merkle tree, we can be in the 40 to 501 byte size. So that's a significant drop in size and fits us easily in the ballpark of what could fit in a UDP response. And on the top, you'll see a graph there that shows the difference between the condensed signature, the short authentication path, and then the large path with the tree, the roots, and everything signed all in one. So there's a big difference in size there overall. Similarly, for the performance, if you take a look at the mean time here, you'll see that we take something that is very long and slow with the SLHDSA signatures and bring it down much more in line with the ECDSA. Now, the benefit here is most of the time you're just doing hashing and comparing hashes, so the performance is pretty good. There's a lot of optimization and support for hashing already built in the libraries and the systems, so we can bring it down with things that are most commonly available and deployed today. All right, so if you take a look now here at the results, the SLHDSA MTL operations fit nicely with the ECDSA and with Hawk in terms of the overall performance. They take it from significantly way high and bring it down to somewhat similar to what we have today. So overall, their conclusions, the data does benefit from smaller signatures using MTL mode, and the performance brings it on par with the current signature algorithms. There's definitely some things we can optimize in terms of only sending the ladders when need be, so we reduce the number of large packets that get sent, make it much more in line with what we see today. And there's a little bit more about that in a moment when we get to the next research. Okay. So we talked about ladders, we talked about condensed signatures. The only question that really remains from the big set here is, how often do we need to get that really big ladder and that really big signature? If the smaller one's good, but we still need the big one once in a while, how often do we need that? With MTL mode, the best possible scenario is you sign once and you never need to sign again. That's not very realistic, but that is taking the most optimization possible. The worst scenario is every single record is its own independent signature. It needs a full large signature. In that case, you're just getting none of the benefit from the larger signatures overall. So what you really want to do is find something in the middle, a batch mode signature where you can sign some records in a set and then sign some more as you need to, every time you get a set of changes. The more batches you have, the more responsive it becomes, so the more frequently the zone will be updated. The smaller spike you'd have in terms of the number of things that have to be added into the set at one time, but then you need to fetch more of the full signatures so that you have an updated set. Fewer batches, less responsive, a little bit more to have to do when you sign, but then overall you need to ask for the large thing less frequently. And what does that mean then? Well, if we take a look at Virginia Tech took a look at the COM zone from CZDS took a look at the inception time periods to see how often the batches are done, and their conclusion was there was a roughly 25% of the zone was signed daily. And so batches seem to make sense in this regard. If you see the top is showing those batches, and the bottom shows when there was the batches with additional records that came into the zone. So a batch could work in these cases. So then the question is, how can we do this with the endurance? How often do you need to fetch? And so they took the expiration and did an assessment on that based on when it would need to be redone or refreshed, and saw that if you have, let's see here, if you have 1 second, so if you sign the zone every second, then on average you'd be able to verify 75,000, not quite 75,000 signatures before you need to fetch a new ladder. So 75,000 validations roughly for every time you need to fetch that big signature. And you'd only need to cache about 14 of those big signatures, or process and cache 14 times those big signatures a day for a 1 second zone signing. Now, if you move that up to like per hour, if you sign every hour and publish, then you can do almost 280,000 signatures that you verify, and about 3.5, so four times a day, you'd have to go fetch a new ladder and cache it to get that same benefit. So for that zone, 4 times a day, you'd have to go get the really big signature or have it be truncated and retried, and the rest of the day, you'd be able to get it over the standard mechanism as it works today. So overall, their conclusions, the condensed signatures, the faster you sign, the more your batches, the smaller the overall number you can verify is, and the more times you have to get a new ladder. So you want to spread that out based on what works well for your zone, how frequently your zone updates. But also, they're doing this amortizes the cost of the the PQ signatures over the zone, so it reduces the overall impact. All right. So in conclusion, we need continued community support to continue looking at these algorithms. We need help looking at especially the new drop-in replacements, and see what works really well for people, what fits within the operations of their zones, because not all zones are the same. We should have a goal where we want to be able to standardize anything that's a PQC signature algorithm that's good into DNSSEC. Perhaps we put it with a mode of operation like MTL mode, so we can reduce those impacts overall of those signature algorithms. We should support a conservatively designed algorithm so that we have a safe fallback, and we can make sure that the overall resiliency of the zone stays, or the resiliency of DNS is maintained, and give ourselves agility so we can change algorithms as we need, or as new things come out or things get broken, we can change. And then finally, with the NIST deadlines coming up in just under 10 years, we need to be thinking about what we want to do now. We need to get research done. We need to start working on standards so that we can be sure that the community has time to update and migrate to a PQC solution before it's too late. And that's all I have. Thank you.
So thank you. Thank you. Come up and ask questions.
Okay, good. Joe Abley, Cloudflare. So one of the things that's always a bit alarming about the idea of these enormous signatures, which applies to MTL2, even if it's not for every signed response, is the size and the amplification potential. So another thing that will take an awful long time, if it can happen at all, is to change the pervasive transport that's used for these things from UDP, where to something where source spoofed addresses is not an issue, so that we can reduce that problem. Because otherwise, this seems like a nightmare. It seems like a step backwards from the point of view of unwanted traffic. So as you continue the conversation about how to sign things and how to generate responses, do you think there's also a need to have a conversation about how we actually carry these things and what transports are used for these algorithms?
So definitely, like, we did some research on, like, if you fall back to TCP, what happens, and your latency goes up, it adds a lot of impact. So again, I think those are all things we need to do research on, but that was part of our motivation with MTL mode, was how much can we keep over UDP? Because if we have to change transports, then we change a lot of assumptions and a lot of other bets, right? And even some
right, but I'm suggesting, but perhaps that's necessary. So rather than just to fall back to TCP, maybe you just plan to live in a world where every one of these queries is pipelined over a bundle of DOT connections or TCP or something, and you never use UDP for this. In fact, maybe it's not allowed to use it with UDP, something extreme like that.
Hi, Peter Lexus Power DNS. Has any research been done on the ladder modes and dynamic answers? So, for instance, dynamic NSEC records, bump in the wire signers, these kinds of things, because I would expect them to have huge signatures because they cannot compute a ladder because they don't know the whole zone.
Yeah. So, like I mentioned, the worst case scenario for MTL mode is signing every single record individually and then having to provide the ladder. So that's not a fit for that. Dynamic answers is going to be a big problem itself because none of these signatures are small, and so yeah, we haven't really researched a whole lot on dynamic answers because the signatures have the same sort of problem. But like MTL mode isn't necessarily for individual record signing, going to be.
Right, but I could suspect people wanting to use the post-quantum algorithms and still have dynamic zones. So is this something that's at least on the something you're thinking about when researching all these things, and maybe discuss with the cryptographers?
I mean, it's something that does need to be researched. Yes.
Thanks.
Shane Kerr, IBM. I actually had a very similar question, but as kind of a subset of that, when you're doing the research and you were looking at performance and packet size, were you looking at other resource consumption on the server, like memory use for signing and validation and things like that? Or is it all just small?
So we were looking at like signing time, memory use. There are some charts for that, but like you see, some of the algorithms do take a lot of time, a lot of resources to compute. There's also a lot of work going on, like at NIST conference last week, they were talking about, constant time performance and side channel attacks and stuff on these algorithms. That's not something we've looked at for DNSSEC because
we don't care about that.
Right. Yeah. Especially if we're not doing dynamic signing, we can do different things, right? So, but good question. Thank you.
Hi, Puneet Sood from Google. My question, to strong +1 to what Joe said, I was going to mention that, but since he's also already mentioned it well, I think that is fine. The additional question I have especially for myself and others who have not really looked at MTL or the implementation, would be this presents the benefits. Can you also, and I've seen similar presentations once or twice before. So what I'm curious about are the operational and other complexities introduced by MTL. It would be good to hear about those aspects too.
Okay. Thank you.
Thank you.
Petr Špaček, SC. I will jump on the Joe's bandwagon. If we assume that the TCP is universally available and it works TCP, what would be the remaining benefits of the MTL? Can you summarize? Because I cannot really discern from the presentation what's just avoiding the big packets because we want to avoid them versus other advantages if we assume that the transport can handle more than 1200 or something.
So the goal of MTL mode is to reduce the overall resource consumption, right? So for one of the big things we wanted to do was see if we could fit in UDP, and so we can get that. It compresses what has to be sent, uses less bandwidth, uses less, but also doing the hashing-based validation is a lot more performant than doing cryptographic operations on every single signature. So we were just amortizing in those cases the cost of, SLH DSA can take several seconds to verify one signature. So if you can amortize that across, thousands or hundreds of thousands of records, then, that performance becomes much better because you can't get into, where your validator is having to do a lot of validation over a lot of time.
So in other words, the transport size is not the only aspect which is improved. That's what they are saying.
Correct.
Thank you very much.
Thank you very much to Joe.